So, welcome to my talk. I'm going to talk about a research project which ended end of last year. It was called UnderwaterINSPECT. Before this, I give you a very short introduction what is Wölfel doing. Then I introduce to the research topic and we'll talk about experiments in the test center for foundation structures in Hanover, and then about the potential of structural health monitoring. And at the end, I will give you a very short impression of the Wölfel solution for foundation monitoring. What's Wölfel doing? We are doing dynamics. I think it's not necessary to explain this little experiment. We are dealing with all kinds of dynamics, and in the technical sense, in most of the cases, we are reducing vibrations. We can excite vibrations too, but normally we are reducing it. The company has about 100 engineers, and we are in a lot of fields of industry. We are doing civil engineering, we are doing mechanical and electrical engineering, mobility, transport, plant and power engineering, and we are in wind energy, and I'm going to talk about wind energy and offshore wind energy today, and we have some products for environmental protection. Offshore wind, these are projects we do. Wind park, we do monitoring in some of the German wind parks, and we have solutions for ice monitoring and blade monitoring too. So this was what's Wölfel doing. Now to the research topic. Extremely high operational demands due to complex superposition of cyclic and stochastic dynamic loading from wind, from waves, and from the operation have an impact on the global stability of foundation structures as well as on welding seams. So that means the failure of the foundation is possible. Especially in Germany, there are regulations from the BSH. This is the German Marine Authority, and they have told that support structures, especially towers and foundations, has to be revised with respect to corrosion, cracks, scouring, and so on and so on. And in the regulation from 2007, every 10th plant has to be equipped with an SHM system. Now this is revised in 2015. They prescribe frequent inspections. That means monitoring and inspection, especially inspection, is a big cost factor, and it's necessary to reduce this cost. With Wölfel, we are dealing with operational based SHM systems, and the basic principle of the SHM system is the analysis of the structural response, which is due to operational and environmental vibrations, and we are using the equation of motion. You all know it. Mass, damping, stiffness govern the dynamics, the dynamic behavior of the foundation. And for us, vibrations are the best source of information. The vibrations contain information about stability, stiffness, wind and wave loads, operational loads, and the mode of operation of a turbine. And there are different ways how to measure the structural response. We are concentrated on accelerations. However, the frequency changes are very small, so we are in a range about 0.5 up to 1%. That means we deal with 0.005 hertz or so, or less. The method behind, we are doing measurement and pattern recognition, and then we come to a decision. I will show you this at the rotor blades. We have about 250 up to 300 SHM systems for rotor blades in the field. In the moment, only with one manufacturer with Nordex, but we are going to others now. So we are measuring the rotor blade with accelerometers and other sensors. Temperature is very important, and we have excitations from the wind, and we have excitations from the machine. And very important is to separate the change of operational conditions from damage. So, because rotor blades are nearly manual manufactured, every rotor blade is an individuum. That means we have to have a self-learning system which first sets its reference features, and thereafter, when the references are found, we are only looking if there is a difference between the reference features and the actual measured features, and only if there is a difference we are going deeper. The residuals are, let's say, show us the illness or the damage of the blade, and we have to evaluate the residuals and do a little statistics, have thresholds, indicators, and so on and so on. And at the end we come to a decision. That means stop the turbine because there's a problem, or you can run. Damage indicators. I'm going to give you a short introduction about the possibilities of two different damage indicators coming from stochastic mathematics. There's the covariance-driven stochastic subspace identification algorithm, which is used in conjunction with output-only modal analysis, and low-order stochastic state space models derived from measured time histories are used. So, and changes comply with changes in the modes of vibrations. And the second damage indicator is null space-based fault detection algorithm. This deals with higher order stochastic state space models, which are derived from measured time histories. And this method is much more sensitive to structural changes than the first one. But at the same time, this is more sensitive to changes with the AOX2. So you have to compensate this. Now I come to the test. This was a more than half-year lasting test. We had a monopile in the test center, and from the test measurement technique we derived the system development. We get measured data from the undamaged foundation. This was in the scale of 1 to 10. From operational modes, we simulated the turbine on top by a shaker. We get peak loads, we change the environmental conditions, and we introduce damages to the structure. And from this we derived the algorithm for an automated operating SHM system for damage detection of such structures and for the compensation of AOX, and we tried to determine which is the sensitivity of our method. We did the following measurements: reference measurement with beginning, and at the same time we observed the soil degradation. Then we varied the load. This means change of the AOX. We introduced the loss of stiffness. This means it's a damage. We looked to the influence of marine fouling. That means change of AOX. We introduced scouring. This is a damage, and misalignment at the end is a damage too. This is the experimental setup. Here this is the tower. We have the electrodynamic shaker, and this is, I think, 6 meters the pile. We have a flange here and the shaker, and you can see here the instrumentation was on 8 levels. I hope the video will start. With this shaker we introduced or we simulated the operational load from a wind turbine. And with this shaker, we were able to initiate a soil degradation. So this was at the beginning of the test. This was not our intention, but okay. So this is reference measurement in soil degradation. This is the power spectral density. The structural response due to excitation with a white noise from between 2 and 50 hertz. And we started with 400 Newton and we reduced to 250 Newton RMS because of this soil degradation. And we controlled the experiment from Würzburg remote. The experiment was done in Hanover. The first point, soil degradation. This is the reference measurement, and you can see here the soil degradation. The first natural frequency was changed. This was around 4.3 hertz at the beginning, and normally there is a hardening of the sediment in offshore. However, we detected soil degradation. The difference is the hardening comes with rammed piles, and we have the pile which was vibrated, and there are a lot of other differences. So the installation by vibration is one. Then there was no time for the settlement of the sediment. There was no water pressure about the sediment. The water saturation of the sediment was not complete. We get, let's say, 85 to 90%, and the frequency were shifted. We used higher frequencies. These are the reasons for this soil degradation. But as you can see, the SHM system is very sensitive for those things. So here these are all measurements, and you can see here this is scouring. That means this is an effect which masks nearly all, and you have to do a lot to find out other changings. Otherwise, scouring obscures all other changes in the signal. Loss of stiffness. We managed this by this flange with 20 screws, and we have reproducible structural damage, and we loosened 2, 4, and 6 screws, and we have our 2 damage indicators, SSI COF, which was running with which used 4 natural frequencies, detect the loosening of 4 and 6 screws, and NSFD was able to detect all with 2, 4, and 6 screws. Fouling. It's not that easy to simulate fouling in such an experimental setup. The possibilities are very restricted because you cannot simulate the computational fluid dynamics or so. So we thought about a special case, fouling in the tidal reach and with low water. That means you have additional mass hanging in the air, and we applied some additional masses. The weight of the pile is about 1 ton, and we applied 4, 20, and 30 kilograms, and we tested our 2 damage indicators. The first did not detect satisfactorily the differences, but with NSFD we get very good information about all changes. Scouring, as I told you, this is masking nearly all, and you have to try a lot to see the other changings. We started with 30 centimeters, and after this we simulated it, and we are now sure we can detect even 5 centimeters of scour. That means the next experiment we will not dig 30 centimeters, 5 is enough. So why is this? These are changings of the boundary conditions of a cantilever beam, and this is a very significant influence. And additionally, we have the soil degradation. This changes the boundary conditions too. And so both indicators are able to detect scouring very well. Last point, misalignment. This misalignment mostly comes from maximum loads like gusts or waves with a 50-year recurrency period, and we used for this hydraulic which we applied to the structure, and the SHM system was first able to detect when this hydraulic is applied, and we found out that you can detect misalignment with accelerometers very well, but the algorithm behind is easier when you are using inclinometers. This is Wölfel's system for foundation monitoring. We measure wind speed, wind direction, power, rotor speed, pitch angle, and azimuth. These are informations we got from the turbine. Wave period, wave direction, maximum wave height, and significant wave height. And yeah, these are the sensors. This is available as a system, and at the beginning you have seen the reference projects. Let me summarize. Foundation structures for offshore wind turbines have to be monitored. Vibrations are, in our sense, ideal indicators of structural behavior and different states of the structure. In a large-scale experiment in Hanover, tests were performed on a foundation structure, and based on this measurement data, a lot of algorithms are developed and the system was tested. I introduced you two different damage indicators from stochastic mathematics, and we detected soil degradations, loss of stiffness, fouling, scouring, and misalignment. And based on these findings is the Wölfel system. And I have to thank the German Ministry of Economic Affairs, which supported this project. Thanks.